Well, I'm Professor Mike Mannery. I'm in electrical engineering. Today, what I want to do is to present some material developed in my lab on feature selection. And the first part of the presentation here is going to be mostly review. And after we cover the main ideas of feature selection, then I'll talk about the method developed in our lab, and we can look at some example applications, remaining problems, and a couple of more applications at the end. Okay, well, in pattern recognition systems, there are several things that can go wrong, and basically, you could have poor raw data. The main blocks in your system could be faulty. You could have poor segmentation, feature extraction, not a very good classifier. In our lab, a lot of the work is aimed at fixing these problems. We don't have any of our own data. We just get data from other people's applications, and then we try to do what we can to optimize their systems. So here, what I'm indicating is we're sort of getting in the middle of an existing system and looking at some of their data, which we're calling training data. So let's look at what is the basic idea of training data. Well, suppose that you wanted to train a system to make buy and sell decisions on the stock market. Now, that's something everybody could appreciate if it really worked, right? Well, suppose that Z1 through Z5 are like closing prices in Dell Computer stock. And so here's 1 week of data here, another week of data, another week of data. If you have a lot of historical data in this form, you could look and see what the trend is in the last couple of days. So maybe a 1 means that you want your system to make a sell decision, and then 2 could mean a buy decision. So here you can note that the price of the stock is trending down on Thursday and Friday, right? And then on the next day, on Monday, it's down some more. So obviously at this point, on Friday, you would hope the system would issue a sell decision, right? Okay, at the end of the next week, you can see that there's a slight trend upwards, and then that's continuing on Monday. So that means you would want the system to give you a buy decision, right? So this is training data. The features or inputs to the system correspond to columns in the data file. And then the rows correspond to patterns or examples. If we did feature selection correctly, we would probably narrow down the number of features or columns and then just use the last 2, right? Those are the most recent numbers, and they would, might give you the best result. Okay, so anyway, that's the idea of, in a nutshell, what feature selection could be analogous to, finding the best combination of your existing columns to make a prediction or a decision. All right. Well, one might question why you need feature selection. Why not just take your inputs, your input columns from your data file, and look at every possible combination. Just design a system for every possible combination of your inputs. The problem there is that if you started off with a large number of features in prime to begin with, and you were looking at a subset of size n, then the binomial coefficient here is this would be the number of possible combinations, the possible number of possible subsets of size n. So, for example, suppose n prime was 3. Well, then you'd have 2 to the third, which is 8 possible subsets, but this is subsets of every possible size. Okay? And it's including the empty set, and then it's including the set that includes all the features. As a second example, we did get some data several years ago from Professor Bebahani in bioengineering. And in that data, he had 90 features. So n prime was 90. Now, if you look at subsets of size 17, there's about 10 to the 18th such subsets. And so that might be too many to really look at in a reasonable amount of time. If you looked at subsets of every size, then there'd be about 10 to the 27th subsets of all sizes to look at. Okay? So, you know, if you think about it, why would we know that 17 was the right number in the first place? Well, we wouldn't, right? Okay, so this is called combinatorial explosion. You might have too many things to look at to finish in a reasonable amount of time. Now, we can think about the components in a feature selection system. First, you might input some training data, and again, this would be like a big matrix of some kind. There's a subset generation algorithm where you basically generate subsets that are going to be considered for evaluation to see if they're any good. Following that would be the subset evaluation function, which tells you how good the subset is. And typically you would save the best subset of each size. And so a subset of size n could be denoted like that. Okay. So that's the basic idea. All right. Well, the subset generation algorithms, there's a lot of them. The best one would be either exhaustive search, where you look at every possible subset, or branch and bound, which is equivalent, but would probably use orders of magnitude less time, and orders of magnitude fewer subsets would have to actually be considered. Plus L minus R is an old method where for a given subset, you add L features to the subset, the best ones you can find. Then you remove the R worst features. So if you add 5 and remove 4, then you're increasing your subset size by 1, right? The floating search is an adaptive version of that, where you adapt the values of L and R, and it's a very good method. A feature ordering approach could be like forward selection. And there, in this case, you would start with the empty set, then you try to find the best first feature for a subset. Then, given that one that's been chosen, you find the best second feature. And so now you have a subset of size 2. And then you keep going and adding on the best additional subset. So there's a lot of other methods, but these are some of the principal ones. Now, if G is some measure of average goodness of a subset, such as one that's related to probability of error, then the probability of error, say, for exhaustive search or branch and bound would be, that'd be the best. Floating search would be the second best. And then you would have L minus R, and then you go down the list and you get to a feature ordering approach. Okay. Well, so, all right. A few comments. Well, feature selection algorithms have been used for decades, and software for feature selection is widely available. Very good and even optimal subset generation algorithms are available. So a logical question at this point would be, what's new? Why am I here talking today? And a couple of reasons. First, subset evaluation functions have been improved. And that's the one place where there's really room for improvement when you're looking at feature selection. So if you go back here, the subset generation algorithms, every 5 or 10 years, somebody comes up with a paper with a slight improvement on those, okay? But the subset evaluation functions, there's a vast room there for improvement. Yes?
Has been used to analyze the game of poker You know, in poker, there is some combination of cards that I don't play it, but are good. Have they been used these methods for that game?
Well, that's a good question. I think there's a lot of ways to extend the application to feature selection. I never considered using it for poker. But, I don't know how to answer your question right now. But if you think about it, if you're trying to look at all possible poker hands that you have and not knowing what anybody else has, well, I don't know. It seems like you'd have too much data, probably. So I don't know how to answer your question right now. But I suspect you could set up some kind of a training set and try something like that. Okay. Well, I want to try to get across the idea, some of the basic problems with existing algorithms. So this look at two methods, and basically method one, which I'm describing here, we're using a good subset generation algorithm, just feature ordering. It might be sequential forward selection that I described earlier. However, here I'm picking one of the worst possible subset evaluation functions, one that's in many, many textbooks, and that would be the use of like a Pearson correlation coefficients. Now, so the idea there is, given a subset you want to evaluate, you just measure the Pearson correlation coefficient of each feature and then add those up. Okay. In method two, this uses
correlation function with respect to class.
Pardon? Yes.
Correlation with respect to classes.
Right. So you could. I don't know how they do that. They could use like +1 for one class and -1 for another class as an example.
Well, you can measure across, I guess, and you can, given the data, you can measure that.
Okay. But anyway, method two, this is an optimal method for the subset generation algorithm. For the subset evaluation function, the best possible one would be like Bayes' probability of error. Okay, so method two should be the best. Now, as an example, this uses some data where we have 4 features unknown to the user. The first 3 are identical. So you have extremely strong linear dependence, right? Now, in real life, that wouldn't happen. You could look at the data file and see there was a problem. But suppose in real life, this could be the negative of that one. But this one could be 5 times that one. This one could, it could be the cube of the first one. They'd all have the same information, and you may not be able to see that. And then the last one is noise. Okay, X is somewhat useful. If you look at method 1, the primitive method, you find a feature, perhaps the first one, and that's your subset, and you have a measurement of the goodness of that subset. Now you find the second feature to add to the subset that increases the value of estimated goodness. And the third one, it gets better. It looks like you're having a great subset, right? And then on the fourth one, the method will detect that noise is not useful. And so there is no increase in the SEF in this case. Well, in method 2, one difference is the SEF is better if it's getting smaller, right? So that's why it's getting larger here. Is the same here. In method 2, which is an optimal approach, you pick one feature and you have a value of the SEF. The second feature doesn't help. You have the same value for the SEF. That's because this method would detect that the 2 features are identical. Okay, and then so there's no improvement anywhere down there, and you would know that just picking one feature is correct. Here, it looks like you need 3 features.
So this SEF is not is it a classification accuracy, or what is SEF here?
Well, like I said a minute ago, the SEF for this method could be the probability of error of a Bayes classifier. And the one over here is a sum of Pearson correlation coefficients. Okay. Now, let's look at a second example. suppose unknown to the user, again you have 4 features. The first one is X, which is somewhat useful, but it has noise added to it. The second one is identical. The third one is a different useful feature plus 2 times the same noise present over here. And then the fourth feature is the noise. If you look at method 1, the poor method, you might get, say, an SEF of 0.1 for that method. Then you add the second feature, even though it's identical to the first one, and your SEF increases. And then you add the third feature, and the SEF increases. Noise, this method correctly detects that the noise is useless. At least it seems like it's not useful. In the optimal method, on the other hand, you might pick Z1 or Z2 first, perhaps. For the second feature chosen, the method would not choose the second feature because this method would recognize it as being useless or identical to the first one. You might choose number 4, a noise feature. The reason for that is that Z1 minus Z4 would be a useful noiseless feature. So the noise can improve your performance in this case, right? The third feature chosen might be number 3 because Z3 minus 2 times Z4 would be Y, which is useful but different from X. If you attempt to add the duplicate feature, you have no improvement or no decrease in the error. So that means you can see that the subsets here are not necessarily nested. So each small subset doesn't have to be a subset of the next one in the list. Here it's different. So even though we have a feature which is noise, the noise would be useless by itself, but in conjunction with the other features it could be useful. You have a question?
Excuse me, if you have the first feature is for example, the second feature is a square of the first feature, and the third one is the cubic of the second one. So in that case, again, your base method gives the worst result in regard of the first method. But still, we know that if we have a feature which is a square and cubic and otherwise, it is a valid feature. How about this case?
Well, actually, I thought about making up an example like that, but I thought people would just get lost and fall asleep or something. But yeah, I consider that. Suppose I had here, I don't know, I could have x squared or x cubed plus some noise or something like that. Well, it would still be redundant. It would still be useless.
But still, it's useful in the matter of if you have an overfitting, we can solve the overfitting by this technique. So in that case, you still have overfitting even though you have just only one feature.
Yeah, well, if it's redundant, it's not going to help. Right? So yeah. But yeah, I think certainly if features are non-linearly dependent, they're still useless. I mean, the only question is whether or not your system can, correctly detect that and then avoid using the redundant features. So anyway, I guess the idea here is that the main idea is that you need a good subset generation algorithm, but you also need a good subset evaluation function.
I have a question again about the correlation coefficients.
Yes.
So is it like you find out the cross correlation between Z1, Z2, Z1, Z3, and so forth? And
well, I think frankly, I can't remember it in great detail, but no, it's more like a Pearson correlation coefficient, among other things, would have a cross correlation between the given input and then the output class decision. And that's the best. I think it's normalized or something like that. But that's what I recall. Okay, now as far as the subset evaluation functions, well, let's let X be a feature subset, and then X sub K could be a candidate feature for possible inclusion into the subset. A good subset evaluation function G would have monotonicity. So if you add a new feature to your subset, if G was error, the error would go down if you add more information. So that's one reason you wouldn't really want to use a validation error. I know people do that, but validation error can go up as you're adding more information. And so in general, you would not want that to happen. Now, example classes of subset evaluation functions. Wrappers, these attempt to design a good classifier and measure a probability of error. Filters, these could be things like scatter matrix separability measures, mutual information, Bhattacharya distance, and there's some others. There's a lot of others besides what I'm talking about here, but these are the two main classes. Okay. Now, I want to give you the reasoning that my students and I have used to design a new method several years ago. We could consider what would be optimal feature selection. We can't do it, but we can think about what it would be. First off, you need an infinite amount of data. However many features you have to evaluate, you would have an infinite number of rows in your data file. You'd use an optimal SGA, such as branch and bound or exhaustive search. For the SEF, you would calculate the Bayes probability of classification error. Okay, now, what would be a useful format to print out your results, if you could get any results? Well, each row would be the subset size first, n. Then the actual subset that had been chosen would be listed. Then the actual probability of error. Okay, so that would be a useful way to print out the information. Now, if we try to get practical, we might reduce the amount of data. So our data file has only NV, which will be a finite number for the number of rows. You could still have a good subset generation algorithm. For the SEF, you could use the probability of error for the data set you have, but where the classifier is maybe still a Bayes classifier. So we've relaxed the size of our constriction on the number of examples in your data file, but we're still trying to use an optimal calculation here. Well, there's a problem. This would not work, and it would not work because if you have a finite amount of data and even if you're putting it through a Bayes classifier, you've lost monotonicity. So if you add an extra feature to your subset, and you have a finite number of patterns, that doesn't mean that the error is going to go down if you have an optimal classifier. This doesn't mean that at all. So using a probability of error would not be the best choice. One solution to that problem would be to, instead of using a probability of error for your classifier, to use a mean square error. The classifier itself could be some kind of approximate Bayes classifier. Okay. Now what else? Instead of using validation error and putting that through your classifier, you would probably have to put in training data. If you put in the training data and you're measuring a mean square error at the output of your classifier, then when you add more features, the error could go down. It can't go up. So, if you have a system that makes optimal use of data, giving it more data results in less error, not more error. Okay? So that's the idea. Now the final details of the method that we're looking at in our lab. We have a finite size data file, a good subset generation algorithm. We're using the floating search at the moment. For the SEF, we would want to use a mean square error for an approximate Bayes classifier. Now, there's many classifiers that people know can be used to approximate a Bayes classifier. There's a Bayes Gaussian classifier, a naive Bayes. There's nearest neighbor classifiers, feed-forward neural nets, piecewise linear network classifiers, even support vector machines. Now, a lot of these can be accurate and get good results if you make the classifiers large enough. As far as fast, none of them are fast, except for possibly the piecewise linear network. And I'll describe what I mean there in a minute. Now, what about monotonicity? The idea of monotonicity is if you add a new feature to your subset, then your error might stay the same, but it can't go up. Okay? So the only, as far as I can figure out at the moment, the only choice is the piecewise linear network. Anything else, you would lose monotonicity. How about speed? The reason why I'm claiming the piecewise linear network could result in a fast evaluation of a subset is because you don't have to pass through the data. If you have an autocorrelation matrix of your features calculated over all your training data, and then there are ways to take the classifier that you design, process the correlation matrices, and get an evaluation of your subset. And you don't have to pass through the data. So that's the whole idea. Okay. Now, what would a diagram for a piecewise linear network look like? Well, if you had an input vector, you could use a distance measure to determine which cluster it belongs to. Given the cluster, there would be an associated matrix. You multiply the matrix by your input vector and get an output vector of discriminant functions. Okay. Now, each individual network here is a linear network, but the classifier as a whole is nonlinear because you know, depending upon your input, you go through different matrices to get your output. Okay. So that's just a general idea. The mean square error I'm talking about would be an average of the desired output minus the actual output of your classifier. A desired output could be 1 if I was like for the correct class, and maybe 0 if the I's class was incorrect. Okay. Now, what else? Yeah, the outputs for our algorithm are pretty much like what we described before. You'd have a number which is the number of features in the subset. The actual elements of the subset would have to be supplied. You'd have a mean square error. Well, people want to know the classification error for a given classifier. So I'd have to print out something here. We could print out a training error or a validation error in the last column. But the actual evaluation is done on the basis of the mean square error. And that's because there's monotonicity. Okay. All right, here's some examples. I have some old data for numeral recognition, hand-printed numeral recognition. And there was 10,000 patterns, 16 inputs. So the data file then would be 10,000 rows, 16 columns of features. There is an additional column that would store the correct class number. And as a hand-printed numeral, the class would correspond to numerals between 0 and 9. Okay, so the error percent that we got, I believe this is for training error. Obviously, it decreases in general as you're adding more features. But it doesn't have to. We were just lucky in this case. The mean square error that's used to evaluate the subsets would decrease. Okay. Now, the actual subsets, a lot of them are, you can see we have nesting. So 6 is an element of every subset. A 9 seems to be an element of every subset. Some of them do become eliminated. Now, on the spur of the moment, I don't know if I can actually find one, but but maybe you can see some. I don't know.
The 3 is in the
3? Okay, there's a 3 there. A 3 there. It's missing here. Okay, so we don't have nesting. That's just sort of illustrating that we have an advanced method for the subset generation. Okay, all right. So that's one example. This is an example from some data that Dr. Bebahani and one of his students had. In this case, they only, since it's a bioengineering example, they only had around 136 examples. And that means 136 patients, right? So, anyway, there was 90 features that he came up with, 136 patterns or rows in the data file. And again, we don't have nesting, I don't believe. I don't want to try to prove that on the spur of the moment, but usually we don't. Now, here you can see that the curve is sort of ragged as you're increasing the subset size. The actual mean square error would be decreasing monotonically, okay? But what this is sort of illustrating is sort of a defect in the approach, and that is that I think it's partially illustrating that there's a lack of monotonicity if you use a probability of error. But it also is illustrating that just because you have a smaller mean square error when you design a classifier doesn't mean you have a smaller probability of error. Those are two different things. They follow each other in sort of a general way, but not point by point. Okay, well, so what kind of problems do we have in our system that we're continuing to look at? Well, there we are. Okay. The sequential forward floating search is what my student Zhang Li used when he came up with the algorithm. This is an approach where you sort of maybe start with the empty set and you add a couple of features and subtract the worst one, and you do that sort of adaptively. That's not the optimal approach to use for the piecewise linear network. It would be better to use the sequential backward floating search, which starts with all your features and then removes the bad ones, and maybe adds a couple of good ones and subtracts more bad ones. So that's one change that we're interested in making. We want to implement fast methods of branch and bound. Also, we want a branch and bound subset generation algorithm that generates the best subset of every size, not just a user-chosen size, right? Because ahead of time, there's no reason the user would know how many features he needs for his application. Okay. What else? We want to make the calculations of the subset evaluation function recursive, again, to speed up what's going on. Well, one thing we've already seen is that wide data files have a problem. Now, a wide data file, by that I mean we don't have enough rows and we have too many columns. So that was the case that we had for Dr. Bebahani's data, right? So if we look at that, one reason that the curve is ragged, in addition to what I said, is we don't have enough examples. A classical problem when you're looking at bioengineering problems. Okay. Now, in the one reason for that is that we have enough coefficients in the piecewise linear network classifier to begin to memorize the data. And the number of patterns that could be memorized would be the number of clusters you have, or pieces, in your piecewise linear network, and then times the number of inputs plus 1. So that means that looking at this, the number of patterns is too small. You could say, on the other hand, the number of inputs, the number of input features is too large. Okay, so we have I was thinking of calling this a fat data file, but, it'd be politically more correct to say a wide data file, right? So anyway, one name for this kind of behavior is a Hughes phenomenon. And in Hughes phenomenon, Hughes noticed a long time ago that given training data, if you add more features, although a mean square error might go down, a validation error can turn around and go up, or at least level out. So that's a very well known phenomenon, and that's good. What you would want to happen is if you add more information, you would want the error to go down. So continuing to talk about wide data files versus the tall data files that are desired. What we would want would be to turn around that inequality on the other page and have a number of inputs small enough so you could not have memorization, maybe much smaller. There's many ways to make a data file tall or have a lot of training patterns compared to the number of input features. One common way is to compress your feature vectors. Another way is to find some way of getting new data. There might be ways of generating artificial data from your raw data. There's a lot of other ways that can be used as well to generate a tall data file. This is just a slide from another old presentation, but the idea here is suppose you had a text reader, and where you put in a hard copy of a page, it's scanned, you segment out words and then characters. And so here, for example, you might have a character 3. Then you do feature extraction. You might have some kind of compression going on. So here, for example, the feature extraction, you might use low-frequency, two-dimensional DFT, discrete Fourier transform coefficients. That would be, in that case, you'd be doing not only feature extraction, but you could say compression. And you would try to pick a transform that reduces the number of inputs compared to what you had pixels. Okay. But in any case, picking the right linear transform for certain parts of your input, would be a useful way to do compression and reduce the number of features you have. Like certainly you'd want fewer features than you have pixels in the raw data. Right. Okay. Another problem is the piecewise linear network, or whatever network you're using, for your wrapper. It might be improperly sized. So you would want to somehow reduce the number of coefficients in your network so that you were in this area here. That is true. But you'd also want to reduce the size in such a way that even the maximum size feature vector is here and not way over here somewhere. Okay. Anyway, here's a third example. This is using some of the data from Professor Liu in bioengineering. And my student Rohit actually did this work. We got the data from Dr. Liu and her students. What she had was breast cancer biopsy data. And what they had is slides, I believe, with the biopsy on the slide. And then they would look at different sections of it and measure the spectrum of the reflected light. And basically they would look at 989 wavelengths of the light reflected from the samples. Unfortunately, there were only 45 examples, so that would be, I guess, patients plus controls. I believe that's the right terminology. So if you think about it, that's an extremely wide file, right? So we'd have basically 989 columns of features, but only 45 rows. So that's a big problem. So what Rohit did is to average groups of the consecutive groups of the wavelengths subsampled the features down to 39. So it's still a wide data file, but it's not near as bad as it was before. Our method, which is called PLOFs, not really a good acronym, I guess. For that, the sizing we had reduced the number of clusters down to 1. And we did end up with the number of features being 39 was less than the memorization capability, which was 44. Okay, now the results we got were really interesting. If you look at the feature index, here I believe the wavelength is increasing as you go to the right. What we saw was that, looking at the average feature curve for healthy individuals or healthy samples and those which the doctor said had corresponded to cancer. If you look at the features that were chosen, those are the solid dots. And so the interesting thing here is that Dr. Liu's students tried to use a slope feature to tell the difference between one case and the other. When we just ran our feature selection on our data, it was tending to pick out features corresponding to peaks on these waveforms. So basically, there would be slope information if you have, when you're looking at consecutive features or consecutive samples there. Also, the sampling rate seems to be greater where there's a greater slope. And the sampling rate is lower when the spectrum is sort of broad and with a low slope, a small slope. So that's sort of interesting. Now, the actual standard deviation of the features in this area was actually pretty large compared to the separation that we have there. And that's what I'm illustrating here. I believe these results are showing the actual piecewise linear classifier results, and it seems to be indicating that we could get basically 90% correct classification. Now, Rohit designed an actual neural net classifier with only a single hidden unit, and it performed well. And it looks like we had basically very good results on the ROC curve. So basically, what I could say is that the desired curve would be, you'd want it to be as close as you can get to 1, even if you're far over on the left. Okay.
These errors these accuracies are cross-validation results or training or?
Well, these are 16-fold validation results. So. Okay, so in any case, it worked extremely well. Now, what I neglected to say is that we selected 7 of the features of the 39 features. Just summarizing results, we had non-uniform sampling of the spectrum, as I illustrated earlier. One implication of this is that instead of using the expensive LRS system to get this to get that spectrum, a much cheaper system having 7 optical filters and a multilayer perceptron classifier could basically replace the expensive system. So there's an opportunity to come up with a cheap system for detecting breast cancer. Okay, now one thing we would expect is that as we get an increased number of patients and controls, the feature selection results would probably change. But in any case, I expect that we'll get better results as we have more data. All right, now for a last example, not everything we do is pattern recognition or classification. We also do things like forecasting. Like one of my students, Kunal, is developing what we could call a weather forecasting system. Among other things it does is forecast temperature based upon information like the past temperature for several days on an hourly basis. Also, the system knows the time of year because it knows the day of the year, right, between 1 and 365. It also knows the time of day, on 24-hour time. Okay, so well, what people typically do in a forecasting system is they say, well, we have data from the current time, and then we go backwards X number of days, we'll take all the samples. Well, that could result in you having a lot of features, a lot of inputs. And not all that information is going to be useful. The further you go in the past, the less useful your information is, if you're doing forecasting. So the question is, how far in the past should you go? And do you need consecutive samples in the past? Like if one idea, if you were trying to forecast the temperature 12 hours ahead, then the useful data from the current time would be 12 hours in the past, right? Because there'd be a 24-hour separation. I mean, there is sort of a 24-hour approximate periodicity in temperature, right? Like the maximum temperature might be around 3 o'clock every day, right? So, but anyway, so what we did is design our system. We did have a lot of data, so we did have a tall data file, but we started off with 120 past hourly temperatures as well as time and day information. After running the feature selection, we found that we could use, say, 75 of the past temperatures. After using the Karhunen-Loewe transform, the KLT, to compress the data further, we were able to reduce that to 55 inputs. Okay. Let's see. Oh, yeah, the KLT, we also use that to compress the outputs from 72 hours for our outputs, 72, right, down to 45. Okay. Now, this is not a great example. This is one where the system didn't work all that well, but you can see that it's trying to work. Okay, it is getting in general the right shape. So it looks like there's going to be applications of feature selection in many applications that we haven't really considered before. Okay. Now, continuing this forecasting example, we can look at the number of inputs chosen divided by the number of patterns that we have. We would want this to be small, therefore giving us a so-called tall data file, right? So after the feature selection, I think we went from this column down to this column, right? So 53 features originally, then down to 35 after the feature selection, and then after the transform down to 19. So all we're illustrating here is that the transform approach and the feature subsetting approach that we're looking at can make a big difference as far as making your data file tall rather than wide. Okay, so conclusions. This method we're talking about, piecewise linear orthonormal floating search, is an effective feature selection algorithm. We've developed it originally for narrow data files where we have a lot of patterns available. We've demonstrated it on 3 pattern recognition applications and 1 forecasting application. That means that it works well for estimation as well as for classification. The method is being modified to work better for wide data files, since there's a lot of important applications where you don't have enough examples. And it's not just bioengineering examples where we run into that problem. another thing, the accuracy and speed of the algorithm is being increased. Okay. Well, that's all I have. Does anybody have any questions? Yes.
Can you go back to the two previous slides?
Sure.
The curve you have. Another one? Yes, this one. And do you have any other curve for the number of that prediction with the 120 features or 75 feature? Because you're just showing here with the 47 feature.
Well, yeah. My student Kunal is just finishing up his master's thesis and everything and getting everything turned in. So he wasn't able to get me an improved figure here. What we wanted to show was, great, if we're looking at 120 past hours, which ones were chosen? That's a perfectly good question, and I want to see the answer to that. I don't have it right now. I know that it's not like you might suspect that you use every hour back to some point and stop. There are gaps. So you have data, then some skipped, and there's more data, then some skipped. And I think the further you go back into the past, the larger the distance there is between one chosen feature and another. But I'm going to have to see our latest data to be sure. Yeah.
Say, in a medical setting, sometimes costs are important. So I guess what I'm asking is if there was a certain probability associated to certain types of feature, and then there were some cost number, then would be like minimizing cost would be an optimization criteria.
Okay. You want to minimize the cost of your system by associating some kind of cost with the different features.
Right. Yeah.
Well, yeah, sure. There are actually that reminds me of something, and that is if you're trying to improve the performance and you have a so-called what I'm calling a wide data file, well, one thing you'd want to do is to reduce the number of inputs you're using. What people typically do is regularization. They reduce the energy of your coefficients, which may tend to reduce the number of your coefficients or the number of your features. So I think that's related to what you're talking about. It wouldn't necessarily be random or anything like that. But yeah, regularization is obviously a perfectly valid way to try to modify what we're doing so that it would work better with wide data files. And as far as minimizing a cost, like a monetary cost or something like that, sure, why not? You could come up with an extra error term to add to the mean square error and then try to minimize that. So I think that's perfectly possible. Okay, so are there any other questions? Yes.
So I understand that if we collect more data, then you can modify your algorithm. But when is the time we say, okay, that's it, then we can use it for the real clinical case?
Well, you'd be more qualified to answer that than me. Right? But
no,
yeah, I'd say this. As you're getting more data, and we run the results again and again, hopefully we would see the performance leveling off at some point. Then, as it's leveling off, then we could conclude that the system is as good as it's going to get. Now, trying to convince the FDA or doctors that we've reached the final system, I have no idea how to do that.
No, but what I mean is once we stop, we say now we know that can be satisfactory. Can you automate it? Which means computer will give us automatic warning. Say that's cancer. This is not.
Oh yeah, sure. Well, yeah. Remember that we've already okay. On the example, we already had a classifier. So this is these results here are for a classifier with the chosen features. So at this point it's a fixed system. So as long as you're giving it the same 7 features every time, then it'll presumably work.
Could I ask, I know this is a little longer, but just you have a one page like A1, A2, A3, that page, that's just fundamental math that I like to know. You mentioned about linear versus non-linear. So you said, I think a little before that, you have the structure for a box of A1, A2, A3. I think that's...
Yeah. That's a piecewise linear network sheet.
Yeah, here. So what do you mean by linear here and non-linear there too?
Well, linear because you're doing a linear transformation. You're multiplying a matrix by the input to get the output discriminants.
So for example, A1 is equal to alpha times X, kind of a format to be linear.
Well, it's a matrix. Like if X had n features in it,
okay.
And then you have out here, suppose you have a vector of m discriminants, then A1 could be a matrix which is m by n.
So then what's the nonlinear sense?
Well, it's not linear because it's piecewise linear. Like if you're, let's see, how can I explain? Suppose you were trying to model a parabola with a piecewise linear curve. Then, well, you might have two straight lines and then connected by the top by a third line. Sort of, and then to make it more accurate, you would use more straight lines. Okay, so if you have a nonlinear curve, you can always approximate it by linear segments connected to each other.
So overall it's nonlinear, but then for the...
Yeah, in any given region, it's linear. And so that makes a big difference when it comes to evaluating the error of a given subset.
So in this case, you basically do an initial classification, some kind of things to determine which region or which linear region you go. Is that right?
Absolutely, yeah.
Okay, so that first branch is nonlinear in a sense.
So your distance function also could be different, right? I mean, the distance that you measure the error could be different types of distances, right?
Yeah, absolutely. There's many different distances that people have developed over the years, including, of course, like a Euclidean distance. And you have a weighted Euclidean distance, a Mahalanobis distance, I guess a city block distance. There's a lot of them. At the moment, I think that what we have, to make this really work properly, I think we have a Euclidean distance, all right, but the inputs have been normalized so that they have all standard deviation of 1. Okay, yes?
In terms of the observations that you show, there's like columns of features and then you have observations, right? So how important it is for the observations to be independent? Sometimes we have in biology, we have repeated data which are statistically not considered independent of each other. So if we have number of observations on the rows, so how does it affect the output of the model if the observations are not independent?
If they're not independent?
Yeah. In the sense, from the same features, you may have like 10 observations.
The design of the piecewise linear network will still work okay. So, for example, it's not like if two columns were identical, that the system would crash or fail or something like that.
Not the columns. Columns are the features, right? So
right.
I'm talking about the rows, which are observations. So.
Well, yeah. Certainly, you would now it's. You would hope that you don't have a lot of duplicate rows, for example, but the rows have to be linearly dependent after a certain amount of time. I mean, if you had 10 columns and you had 20 rows, well, doesn't that mean that 10 of your rows are dependent? I believe it does. So the thing is, the processor we have, the piecewise linear network, is nonlinear. So the fact that you have input vectors that are dependent doesn't really, by itself, make any difference. Okay, well, anyway, I think that we all have...
Okay, let's thank them.